general questions, probably. I don't see you. Oh, there you are. You're under C. It's okay. I, you know. Any questions or problems? Okay, whoops. We were talking about the Arrhenius equation. And again, in its classic form, ignore the slides as I jump around. In its classic form, right, it looks like this, right, where really what I have now are two new reaction parameters, the activation energy and the Arrhenius constant or collision frequency factor. And so if I really want to fully functionalize my Arrhenius equation, right, which is really trying to fully functionalize the rate constant, I need to find those two things. And so we got as far as saying, look, what that really means is I need one extra data point. In some sense, what I'm doing is trading K for EA and A, because again, the rate constant is very temperature specific. It's not really a system parameter in a generic sense, it's a very specific one. And so, right, my data set really now boils down to, in this particular case, knowing order of both reactions, or both reactants, excuse me, right, as well as knowing now A and EA, right? And so from either an algebraic or experimental sense, what I really have are four things I need to know, which is why I have 4 experiments that I did. All right. And so, you know, the order's first typically, right? And then that allows me to calculate the rate constants at the different temperatures, which then allows me to get EA, which is sort of where we left off, right? Now, in a very narrow sense, all I really need is EA, right? If I want to deal with one temperature at a time, once I have the activation energy, I could always plug in to this expression, right? My 2-point Arrhenius equation, as I call it, and find EA at any other temperature I want, right? I mean, all I need for this to work is to know EA, because I always know R. And if I know 1 K and T, I could find K at any other T I want, right? And so in the very narrow application that I just want to calculate the rate at a single temperature, I really don't need anything but the activation energy. And so here I did it for 400 kelvins, right? I just swapped out one of the K values that I knew for my new temperature to calculate the new K value. And a lot of times that's all I'm trying to do, right? I have a temperature at which I'm running this reaction. That's the only one I care about, right? More generically, if I just wanted to make a statement completely generally about the kinetics of this reaction, I really need A and EA, right? But again, once I have EA, I could, if I was so inclined, right, use the Arrhenius equation to calculate A, right? Because at this point, you know, R is R. I have a whole bunch of different Ks and Ts. Pick your favorite one. If I know the activation energy, the only thing I don't know is the Arrhenius, right, factor. So again, from a purely experimental standpoint, at this point, I had 2 different temperatures, Ks, or 4 different measurements of K. If I really want to do this accurately, right? I might want to calculate the EA 4 different times and average them, but, you know, just for demonstration purposes, I picked one of them. So, you know, at 400 kelvins, K was 0.96 atmosphere to the -3, seconds to the -1, more on that in a minute, right? So I can actually plug that along with my EA back into the Arrhenius equation, and I will get the value for A. Right. In this particular case, 6.1, again, atmospheres to the -3, seconds to the -1. As always, please, 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 right, pay attention to the units. I should have a sliding scale for point deductions for failure to cancel units, since there was a lot of that on the first sprint synthesis, right? If this is in joules, so must R be, right? Whenever energy is involved, it has to be kelvins, right? And if I follow through and cancel the units, right, this whole thing, my whole exponential term is unitless, right? I have joules per mole kelvins divided by joules per mole kelvins. And so the units of A are the units of K, essentially. Right. And that would allow me to essentially write an equation that rarely gets written this way, but could be, which is I could write the rate law embedding my generic Arrhenius calculation of K instead of a single K value. Right. And that again is really my goal, both in kinetics, right, and in the rate law specifically, right? I want my rate law to be able to give me the rate under any set of conditions. And the conditions that matter most, right, are concentration, or in the case of gases, that would be pressure, right, and temperature. And here they all are, right? Here's my temperature, kind of lost amongst the other units. There's my concentrations, right? Written this way, pick your favorite temperature, pick your favorite concentration, I can tell you the rate, right? And so that is the most generic expression for rate I could have. In practice, like I said, nobody tends to write it that way, right? There's a tendency to sort of treat the K calculation as separate, right? And so the rate law is usually written just in terms of the K, right? And then K separately is written as the Arrhenius equation, right? But in fact, the whole point of the Arrhenius equation is to give me the K I need in the rate law. And so it's a little ungainly to write it that way, but that's really my goal. That is everything in one easy to use, hopefully, algebraic expression that gives me the rate no matter what. Yes, no, maybe? Questions on that? Since I'm all about the units, right? I should make a statement about the units. Right. K has units. Right. What it does not have is the same units all the time. Right? Because the units end up having different concentration units based on what the orders of the reaction are. Right? basic algebraic rules, right? The units on the left-hand side of an equality or an equivalence have to be the same as the units on the right-hand side, right? And so if I'm a third order, right, rate law, the rate is always going to be either, well, one of three things really, either moles per second, atmospheres per second for gases, or molarity per second for solutions, right? And that means my amounts on the right have powers to them because of the orders. So in this case, I have a rate of molarity per second. I have a concentration in molarities, which is cubed because of the order of the reaction. And so to get molarity per second on both sides, in this particular case, K has units of M molarity to the -2, seconds to the -1. If I change the order, right, or I had two different things, right, I now have more molarities in my rate law, which means I have more molarities in the denominator of K, right? And so K's units change with every reaction because the orders are different. Right. Now that is not problematic, right? I can always just follow the units in my calculation. The only reason I really bring it up is because of the inconsistency in those concentration units, right? They are sometimes just left off, right? Because they're automatically there based on the orders of the reaction, right? What really needs to be stated in K that is unique to K is the time base, right? There's going to be molarity to the -2, 3, 4 based on orders, but that's relative to the concentration part of my rate law. The only place the time really enters in is in the rate constant. And it matters whether it's seconds or minutes or hours, right? I mean, if the rate is 1 per second, it's 60 per minute, right? And so K is what brings the time base in. So a lot of times, right, K is written just as the time units. It's reciprocal time, right? That is not meant when it happens to imply anything about the order of the reaction, right? Because you would also get reciprocal seconds if it was a first order reaction without ignoring the units. But a lot of times they are simply ignored and not written because the only thing I really want from K is to know what the time base of my measurement was. Was it seconds? Was it minutes? Was it years? Right. And in a similar sense, a lot of times the Arrhenius factor, right, is only written in terms of the times because the same basic problem, right? Technically, the units of A are always the units of K, which means they have different numbers of concentration units depending on the orders of the reaction, right? But it's the time base, which is the most critical element here. So a lot of times the molarities are left off. Yes, no questions on that before we leave the Arrhenius equation behind? Anything? Anything? Okay. The calc-based chem. It's all calc-based. There's one other little thing, right, that we could add to our kinetics. And it really, I've mentioned it before without specifying it, right? I said that there were really two ways we tended to get the orders of the reaction and to construct the rate laws. One way was that method of initial rates. This is actually the other way, right? This is, for reasons I'm about to show you, my less favorite way. And you'll see what I mean in a minute. But what this also does do, which the rate law itself doesn't, at least not directly, is allow me to actually watch the reaction in time, right? My rate law gives me the rate at a very specific set of conditions. What's the concentration? What's the temperature? In some sense, by itself, even that number is of limited utility because, as we've been saying all along, rates change, and they change because the concentration changes. And so my rate law will always give me a snapshot in time, right? This is what the rate was at 298 kelvins when the concentration was 1 in 1. But if I wait a minute, the concentration is 0.99 and 0.99, in which case the rate is less, right? And so there is a active time base to what's going on with my reaction. And really the whole point of my integrated rate laws is to allow me to access that time parameter. And it does rely on calculus. And no, I'm not making you do the calculus since calculus is not a prerequisite for this course. But for those of you that speak calculus, I will show it to you. For those of you who don't speak calculus or have bad experience with calculus, consider this your trigger warning. Go get a soda, come back in 5 minutes. We'll be back to algebra, right? But an integrated rate law is quite literally an integrated rate law. The integrated part is the calculus part because the rate of reaction is really a delta-delta, right? The rate is change in concentration over change in time, right? For those of you who speak calculus, right, calculus really just comes from shrinking my deltas to infinitesimally small, right? And so if I do that, I can turn my delta-delta into a small delta, right? A ddt of the reactant concentration, right? If I do that, my rate law essentially becomes, don't panic, an integrable differential equation, right? Because my rate is now a differential of the concentration. And so if I took a simple rate law, like a first order rate law, and I rewrote it as a delta-delta, in this case, the time derivative of A, right? The rate of reaction is really the time derivative of A, and that equals K times A, right? I can actually integrate that. If I collect the time terms on one side, which is K, and the concentration terms on the other side, which is the concentration of A, is the only thing I have here, right? I can integrate both sides of that. And as you may know, right, since K is a constant at constant temperature, right, I'm really just integrating dt, which is just a T, and dA over A is the natural log. And so if I actually integrate my rate law, I end up with what's known as the integrated rate law. Pretty literal, right? Which is really now just an algebraic relationship in time, right? That allows me specifically to essentially track the concentration of A in time, right? Because again, for a given temperature, I know this, right? And of course, as I've been fond of saying, you have to be really lazy not to know the initial concentration of your reactants. I mean, you're the one who started the whole process, right? And so what does that tell me? It tells me pick any time you want. It tells me how much A is left, right? And so, I'm going to refer to this as the independent variable, even though I technically don't have a dial on time, I can wait, right? And so what this equation really tells me is what the evolution of the concentration of A is in time. Right. It is worth noting, and I will note it again several times, right? This could be a more complicated reaction, right? I mean, it could have been, A plus 2B yields, 3 C's and a D, right? The fact that it is only first order in A doesn't mean A is the only reactant. Frankly, the fact that it's first order in A doesn't mean, right, that there's only one A in the reaction, right? But regardless of what's in the reaction, the only thing my integrated rate law can track is the species that the rate law depends on, right? And what I mean by that is if this was my reaction, let's face it, everything's changing. And in the context of the reactants, which there are now 2 of, A is changing and B is changing. And frankly, most of the time I care more about the products because that's what I'm trying to make. And so C is changing. But even if I care only about C, the integrated rate law only lets me watch A, right? Because A was the only thing the rate depended on. Right? The good news is if I care about C, I can get it from stoichiometry, right? If I know what happened to A, I know what happened to C. But I do not directly get that from the integrated rate law because the integrated rate law is blind to everything except the one thing the rate law depended on here, which is the concentration of A. Right. And so integrated rate laws can be powerful and useful tools, but we can't make them more powerful than they are. Right. It is frequently written in the slightly adjusted form where I put the initial concentration of A on the right-hand side, because if I do that, it looks like a straight line, right? Where this is Y, whoops, right? This is X, this is the slope, and this is the intercept, right? And again, in strict experimental and graphical parlance, the X should always be the independent variable and the Y should be the dependent variable, and that's what happens here. I've got my clock running, not that I so much control time, but it's my independent variable and the concentration is changing as a result, right? And so I can use this graphically, and I will in a minute. I can, of course, also use it algebraically, right? So, for example, if I had a rate constant at 298 kelvins, right, and I know how much A I started with, this expression will tell me exactly how much A is left after any time I pick. In this case, I picked 1 minute. Right. Again, as always, beware the time or the units. In this case, the unit I'm talking about is the time, right? K and T have to have units that cancel, right? And so if my K is in reciprocal seconds, my time needs to be in seconds. If K is in reciprocal minutes, my time needs to be in minutes. All right. In this case, my K was in reciprocal seconds. And so 1 minute is, of course, 60 seconds. And so if I plug and chug it, what it tells me is that 1 minute into the reaction, the concentration of that species has dropped from 0.25 molar to 0.102 molar. And we'll see hopefully an example later today. It'll be close, right? Once I know that, I could know what the concentration of everything else is, right? Because if A changed, stoichiometry tells me what happened to B, C, and D also. Right? Yes, no, sir. More calculus. I'll get to that sort of in a second. Okay. But the generic version of his question, for those of you at home, you didn't hear the question, so this will be the only version of it. Right. The integrated rate law I have here depends on the rate law I integrated. Right. And so this algebraic expression only applies to first order rate laws. If I have a second order or a third order rate law, it's going to integrate differently. If I have a rate law that depends on A and B and C, it's going to integrate differently. Right. And so, you know, good news, bad news, right? If I know the rate law, which again is usually my goal was to determine the rate law, so I hope I did, right? The integrated rate law is automatic based on the rate law because it's only going to integrate one way. On the other hand, every different rate law has its own unique algebraic relationship depending on what the integration yields, right? And so, right, we'll look at a couple other ones in a minute, but I do want to point out the graphing side of this, right? Because it works both ways. In this case, I knew the rate law was first order in A, and so this must be the integrated rate law. It works the other way, which is if that line fits, if I were to plot the log of A versus time, and it's a straight line, then it must have been first order, right? Which is why I say this is the other way I could have gotten the rate law, right? If I make the graph, it gives me the order. It fits, it must be first order in A. It also gives me the rate constant. It's the slope, or technically negative the slope, right? And so the other way I could determine rate laws is to make the graph, right? This is a very different experiment than the one we did for initial rates, right? When I use initial rates to solve for the rate law, I've got a bunch of different beakers that all have different initial concentrations. And I'm measuring the initial rate and then throwing them out. In this case, it's a one beaker experiment, right? I throw the reactants in a beaker and I am monitoring somehow the concentration in time, right, of the reactants and the products, right? If I don't know up front what the order of the reaction is, I might need to monitor A and then calculate by stoichiometry what happened to B and also, right? This works best if you have something that's spectroscopically measurable, right? I mean, you did the kinetics lab. The kinetics lab you did was based on color change, right? You used the potassium permanganate, which is purple, right? But you were using it in a binary way, right? It's either purple or it's not. If you stuck it in the spec 20, you could measure just how purple it was, right? And so you would see essentially the absorbance of light changing in time, which would directly correlate to whatever the colored species was that was absorbing light. Right, so it's a very different experiment, but still designed to get you to the same point. What's the rate law? What's the rate constant at that temperature? Right, and so if I plot log of A versus time, if it's first order, it should be a straight line. And of course, when you get to make up your own data, woo! R squared of 1. Right? And again, the slope is negative K. And so I got the order by the fact that it was a straight line, and I got K from the slope. And so this time I started with the integrated rate law and constructed the rate law instead of the other way around. Right? I don't really prefer that as a method. I mean, if you've got infinite accuracy, that might overstate it. If you got really good accuracy in an experiment, it works fine. The problem is degree of fit, right? Here's a different reaction, right? And I made up the data, and you don't really need to know what the data is. There's the graph, right? And so my question has to be, did it fit? And you've been in the lab, you probably even made a graph or two, right? If you got 0.93 for the R squared, did you write up your lab report or beg for more time to redo the experiment? Right? 0.93, especially with an experiment that might have significant variation in it, is not horrible. Right? So it would be very easy to conclude that that does fit. Right? The only thing that makes me even slightly suspicious is I could draw a curve through here, through the data points. And so it looks a little less like random deviations from the line. But honestly, again, depending on how accurate my experiment was, I might decide that's a good fit. When in fact, there are other integrated rate laws that fit better, right? And so the reason, right, that I don't think this is the preferred method, right, is you would really have to make every graph possible and find the best one to be sure that you had the right rate law, right? Whereas the method of initial rates is far more deterministic. I go through, I did the experiment, I calculate an order of 1. Now, if it's a really sloppy experiment, maybe the order was 2 and I screwed up. On the other hand, my experiment told me it's 1, right? And so, you know, you redo the experiment. If it stays 1, you're happy. Here, I've always got the problem of having to make multiple graphs. In the age of computers, this is not horrible, right? It's just a software package on your spectrometer, right? But it is a little less definitive than the method of initial rates, right? And so it really becomes a question of what all the other possible graphs are. And so without boring you with the calculus, right, if your reaction were second order, same thing, right? Substitute dA dt for the rate, get the A's on one side, the times on the other, K and T, integrate it, you get this algebraic expression, which again is essentially a straight line. Now the slope is K, right? This is the intercept. I'm graphing now 1 over A versus T instead of the log of A versus T. And if I do that with the data I just had, this data, right? Again, in this case, because I made it up, hey, look at that fit, right? Even though it doesn't fit first order horribly, it fits the second order much, much better. I'm 0.998 on the correlation coefficient, right? And so it fits the second order integrated rate law. It's a second order rate law. Right. Right. And to the earlier question, this is where it starts to get complicated, right? Because I could be 0 order in A, or first order in A, or second order in A, or third order in A, or fourth order in A. And if there's a B involved, I could be first order in B, or second order in B, or third order in B. or some combination thereof. I could be zero order in A and first order in B, or zero order in A and second order in B, or zero order in A and third order in B, or first order in A, first order in B, etc. Right? So the number of graphs I'd have to make to be really, really sure I had the best fit is rather large. Right? And so it's not my preferred way to find the rate law. If I have the rate law, right, then the integrated rate law is automatic, and it does give me a way to calculate the concentration at different times, which is my preferred way to use this. Right? I could use it to find the rate law. Personally, I prefer not to. But if I got the rate law from method of initial rates, then I know what this algebraic relationship is, and I can calculate the concentration at any time, which is kind of what I care about. Right? For a reason, right, that may be less obvious unless I make a graph. We'll come back to that. Let's try to make a graph. There's nothing easier to read than one of my free-form graphs. Right, so let's say the reaction is, whoops. Right. Oh, hang on. This is my one complaint about Zoom. The display settings. All right, so let's say it's A plus 2B yields 3C. Now again, let's say all right, let's say, C is, expensive drug. This is the thing I'm trying to make, right? Again, I'm only going to be able to track A or B using my rate laws because they're the reactants. Stoichiometry will get me there, but there's essentially three graphs I could make. Right? One I'm measuring, the other two I'd have to calculate. So if I'm measuring A, right, what I'm going to see is, some change in time. How rapidly it's changing depends on the order. B, is going to do something similar, but it's going to do it twice as fast. And then C is going to go up. Right? But here's the thing about my graph. Right? If I get rid of all the graphs and just go to one, right? Most reactions end up doing something like this. Right? Meaning they don't just get to 100% yield and stop. They also don't get to 100% yield typically in a very linear, direct fashion. Right? And so my integrated rate law can tell me how long it takes to be 90% done, or 95% done, or 80% done, right? Because no matter how valuable this is, right? If this is, we'll start at 100%, right? If this is 10% left, and it takes me, an extra, I really can't draw like this. I have a new tool for that. I should try it out. Right. If it takes me twice as long to go from 10% to 8%, I didn't gain a lot. And time is also money. right? And so the integrated rate law can really tell me how long I want to run my reaction, because it's typically asymptotically approaching zero for the reactants, which means it's asymptotically approaching 100% for the yield. And it may not be worth 6 weeks to wait for the extra 1%. Right? And so the integrated rate law is useful to me as a way to sort of plan out my reaction. Right? The book only looks at 3 specific cases because, as I say, once you start mixing A's and B's in multiple orders, the calculus gets complicated. And all I'm really doing is introducing more algebraic expressions by the time somebody does the calculus. And so it's a different functional form, right? But I'm going to do the same thing with it, regardless of which functional form I use, right? And so the only ones the book looks at, and therefore the only ones we'll look at, are 0th order, which are kind of rare as reaction goes, right? Meaning the rate is actually constant in time, right? Because it's A to the 0 order, 1st order, and pure 2nd order. It does not look at any of the mixed orders. You need to do partial derivatives, and you get more complicated algebraic relationships. But again, I'm going to use them the same way. So, right. So, right. Here's my data set. Right. If I'm trying to use this to find the rate law, again, I mix up one reaction and I monitor the concentration of something in time. Right. In this case, it was the nitrogen. Right. Now, again, if I included mixed orders where chlorine mattered, or 1st, 2nd, 3rd, and 4th orders, my number of graphs gets large. Since we're only dealing with the 3 orders, there's 3 graphs I will look at. The 0th order rate law graph, the 1st order rate law graph, and the 2nd order rate law graph. The 0th order rate law graph is a direct linear dependence on concentration. As we saw, the 1st order rate law gives me a logarithmic dependence on concentration. And the 2nd order rate law, right, gives me the inverse dependence on concentration. And so again, it really becomes a question of what the best fit is to one of those graphs. Right? So if I plot the 0th order line, which is directly the concentration of nitrogen, I don't know why it says hydrogen, copy and paste error. This concentration of nitrogen versus time. Again, I don't get, a ridiculously bad fit. You may have fit your own data at one time where it was no better than a 0.86, but 0.86 not terribly good. Right? If I do the reciprocal concentration, I get a much better fit. So I feel confident at this point in throwing out the 0th order line. Right? It's 0.966. That's pretty good. But again, in this case, it actually turns out the 1st order fit is better, which is the log of the nitrogen concentration versus time. I'm at 999. Because again, I made up the data, right? And so again, based on those 3 graphs, the best fit straight line is the 1st order line. And so the rate law I would conclude is 1st order in nitrogen and 0th order in chlorine. Right. Yes, no. I do have one useful problem, which I will save till Friday, not to hurry through it. right? I will point out you can sort of make the graph without making the graph. And I kind of bring this up because this is, again, something of a useful sort of lab trick. I mean, these days you might very well have the computer in lab and you could, throw your data in Excel and make the graph as you go, right? But if you've got just a calculator, you can sort of fake make a graph, right? By essentially looking at what the slope of the line should be, right? If I'm plotting nitrogen versus time, right, the slope of the line is the change in nitrogen over the change in time. If I'm plotting log of nitrogen versus time, the slope of the line is the change in the log of nitrogen versus time, right? And so you can sort of see how good the fit is if you essentially look at the slope at each of the data points, right? And so we used to do this a lot when I was young and had hair, and there wasn't a computer in the lab. I mean, there was, but they were so slow back in the day. You should have seen what we had for mainframe computers when I was in college. But now your phone can probably make a graph just by you talking to it. I don't know. Soon enough, right? So again, there's my data, right? I'm measuring nitrogen versus time. The 0th order line should be directly the change in nitrogen versus time. So if I just look at adjacent data points, right? So between 0 and 5 minutes, right? I look at the delta T and the delta concentration, final minus initial just for consistency. The first order line would be log of nitrogen versus time. So I take the log of the 5-minute data minus the log of the 0-minute data. And again, the second order would be reciprocal. If you do that, and again, this is just kind of a useful trick. In some ways, this is more indicative than my graph, right? Because when I plotted my graphs, they didn't look horrible in terms of the R squared, right? I mean, that didn't quite fit. But if you actually look at the slope at each point, what you see is the one that fits is jumping around a little bit, but they're all in the same ballpark, right? Whereas if you look at the 0th order line, it is actually changing, right, fairly consistently in one direction. Same with my second order, right? It's getting monotonically larger, and it's not just jumping around, right? And so even from just looking at those differences between the data points, right, I can conclude even without making the graph that the first order plot is going to be the best fit. Right. It's not a bad little math trick. Right. But again, if I'm looking for the rate law, I prefer the method of initial rates. Right. But once I have it, I could use the integrated rate law, and that is our last example, which sadly must wait till Friday, when it will be a balmy 28 degrees. In the meantime, have a happy frigid Wednesday. If you have questions or problems, see me. I look forward to reading your project papers on top of the other 400 papers I have to read. I should have thought this through when I made these assignments.